And let's go ahead and get started. Okay, so 9.2 is a section, it's called independent probability, okay? So is probability important kind of in understanding life? Probably. See what I did there? All right, I actually think it is. I think that understanding probability actually can impact your life in a great way. I think that this lesson is kind of the building blocks to some important stuff in your life, okay? So the definition of probability is the measure of how likely an event is to occur. Probability is measured between 0 and 1. It can be expressed as a fraction, a decimal, or a percentage, okay? So I have this little chart here that's color-coded. I really like this because 0 you could see is impossible, and then 1 or 100% is certain. And then most of life is like somewhere in between that. So we have like a 0.25 here is 25% or 1/4. And then as likely as not would be a 50% or 0.5 or 1/2. And then likely is like 3/4 or 0.75 or 75%. All right. All right. So formula for probability is desired outcomes over total outcomes. All right. Desired outcomes over total outcomes. So it's pretty much what do you want to happen? What do you want to have happen over what's everything that could possibly happen? Okay. So what do we want to happen over what is everything that could possibly happen? Like it says before, this can be expressed as a fraction. So you can see like we're for 1/4, 1/4, or 0.25 as a decimal, or 25% as a percentage. Okay. So let's practice with some super simple ones now. So let's say we roll a 6-sided number cube. So we just roll 1 dice, find each probability. And so this is how they write it, P parentheses. So let's read this like the probability of rolling a 5, okay? So how many, so we're talking about a 6-sided number dice. So it's like a cube. One of the sides says 1, the other one says 2, the other one says 3, the other one says 4, the other one says 5, the other one says 6. So how many of those are a 5? Well, there's only 1. And then how many sides are there total? 6. So 1 out of 6. Nice and simple, right? Now, remember though, that we could also state that as a decimal and a percentage. Now, actually on the Schoology, on the puzzle piece we'll do tomorrow, I think it's actually a percentage. So I'm gonna show you how to do this as a percentage. So first of all, you would just divide it in your calculator. So I just took my handheld calculator and did 1 divided by 6. And when I did that, it said it was about 0.167, okay? So that would be another way to write it. And then to change that to a percentage, we just move the decimal place to the right twice. And so it would be 16.7%. So I don't even want to box that one up because all 3 of those are correct. But I'm just telling you that on the puzzle piece, it'll probably be the percentage. But it's good that you know that all 3 are actually correct, all right? Okay, next up, part B, the probability of rolling a 3 or a 5, okay? So I could get a 3 or I could get a 5. So how many of the sides are a 3 or a 5? I would say 2 of them, the 3 and the 5. So there are 2 possible ways I could win that, but there's 6 total. I could also write that as 1/3. Sometimes I don't like reducing the fractions on these ones because 2/6 is actually kind of more descriptive of what's going on. Like I have 2 out of the possible 6, but it's also fine to reduce the fraction. So it's kind of okay either way. And then if I type that in the calculator, it's going to say 0.333. So that would be a 33.3% chance, or 33.3% probability. All right, next up, the probability of rolling a 7. Well, if our numbers are going 1 through 6, I would actually say the probability of rolling a 7 is 0 out of 6. So as a decimal, this would be 0, and as a percentage, it would be 0%. So remember, 0 means literally impossible. Sometimes people say the probability of 0, the probability of something is 0 when it's really a little bit more than 0. So like, for example, when I was in high school, like, and I asked my crush out on a date, it seemed that the probability of her saying yes would have been 0. In actuality, it was probably like 1% chance she would have said yes. I never found out because I was too scared to go through it. But I in my mind saw it as a 0% when in fact it was probably a little bit more than 0. Okay, so it has to be like literally impossible for it to be 0. Okay, most stuff is not a probability of 0. It's probably a little bit more than that. All right, next up, we need the probability of rolling a prime number. Now we would have to know between 1 and 6, what are the prime numbers? So the prime numbers here between 1 and 6 are 2, 3, and 5. 1 is actually not a prime number. A lot of people think 1 is a prime number. It's not. A quick side note here. You guys know, you know when we do this thing, like when we do this and we break it down and we say like 6 and 10 and we say like 2 and 3 and then we say 2 and 5. So what we're doing when we do that, this is called prime factorizations. We're trying to find the prime numbers. And so all the numbers that kind of show up at the end there that you can't break down anymore, those are prime numbers. So my question to you is, have you ever seen a 1 when you're doing that? No, right? Because you don't really use a 1 because it's not a prime number. Is 6 a prime number? No, because we could break it down further. So prime number means when you're doing this, like what are the numbers that you can't break down anymore, okay? So that would be 2, 3, and 5, right? All right, so that means we have 3 out of 6, which could also be 1/2, which would be a 0.5 as a decimal, and would be 50%. All right, and then lastly here, we need the probability of rolling a number less than 10. So if we're rolling a dice and it has the numbers 1 through 6 on it, I would say that all 6 are less than 10. So I'd say that's 6 over 6. As a decimal, that would just be 1. So that would be a 100% chance that that happens, okay? Awesome. Okay, next up, we are going to learn about complements. All right, complements. So this is like when I tell my wife that she looks nice. Nah, just kidding. Well, I do that, but that's not what we're talking about here. We're talking about mathematical complements, okay? So the complement of an event in probability is the set of all outcomes that are not the event, okay? Now, when I say the word complements, you might be thinking about, like, remember in geometry, you had complementary angles. Those are angles that add up to 90, okay? And so that is certainly true for geometry, but for probability, complementary means they add up to 1. So I think that that's still kind of connected to the geometry piece, because in geometry, like a right angle, 90 degrees is like kind of a full angle. You know what I'm saying? Like if you think about it, 90 degrees is kind of a full angle. So in probability, like adding up to 1, that's like complete, okay? So probability of an event, so the probability of something happening plus the probability of it not happening adds up to 1, all right? Or in other words, another way to look at that is the probability of a complement equals the 1 minus the probability of the event. So I'll give you a good example here on number 2 that I think you guys will understand logically and see how it matches up with that. So A news broadcast says the probability of rain tomorrow is 60%. So what's the probability that it does not rain? Okay. Now, I think that most of you guys logically, if you just think about that, you get that the answer is 40%, correct? If there's a 60% probability that it is going to rain, that means if there's a 40% chance that it does not rain, right? It's just kind of the other piece of it. So obviously, it's always going to change how those are split up. Maybe it's 70-30, maybe it's 50-50, maybe it's 60-40 like it is here, but it always adds up to 1. If I really wanted to show my work here, I would say I would kind of use this formula right here, like 1 minus the event. So I would say 1 minus, and then the event is 0.6. I would have to convert that to a decimal. And so that's going to give me 0.4, which would then translate back to 40%. Do I need you to show that work right there? Not really. Like if it's simple like this and you can do it in your head, I think that's fine. But I'm going to go ahead and show it on this one, because when we get to some more difficult questions, it'll make it easier when we kind of think about that, okay? Awesome. Another quick note I always like to point out here. So the news broadcast says the chance of rain tomorrow is 60%, right? And let's say it doesn't rain tomorrow. Do you know what people would say? They would say that the news broadcast was wrong. Now, I disagree with that. I do not think that the newscast was wrong, even if it doesn't rain tomorrow. Can anybody kind of think about this for a second? Maybe you can write it in the chat. If it doesn't rain tomorrow, even though they said 60% it's going to rain, why would I say that they're not wrong? They weren't wrong. Boom. So Danny in here says they didn't say it was 100%. They did not say it was certain it was going to rain tomorrow. In fact, 60% is barely above 50%, right? So they were kind of saying it's kind of a toss up here. Like, it might rain, it might not. I don't know. Yeah, so someone else in the chat said because the 40% was right. Yeah, I like that explanation too. It's like, don't mistake improbability with impossibility, right? Even if something is 10% likely to happen, like 10% chance stuff happens all the time. If you did something 10 times, it would happen once, right? You would expect, okay? So don't think that something improbable happening is crazy, because it's not impossible, it's improbable. You know what I'm saying? Yeah, okay. Next up, we got an important formula here that we're gonna address a lot here, okay? So we're gonna now talk about independent events, okay? So if event A and event B are independent events, then the probability of A and B, and remember we learned last section that this symbol really means and. You guys remember that one? And it's like, I need this to happen and that to happen. As opposed to the other way around when it looks like the U, that was or, okay? And then this one is and. And the formula here is we're gonna multiply together the probability of A times the probability of B. All right, so let's go back to our kind of rain thing here, okay? So let's say the news broadcast says the probability of rain on Saturday is 60% and Sunday is 70%. So what's the probability that it rains on Saturday and Sunday, okay? So for this one, we're gonna multiply together 0.6, which is the probability of Saturday, times 0.7, which is the probability of rain on Sunday. If you multiply that out, that gives you 0.42, which I would then translate back into a percentage. So I would say 42% chance it rains on both days. So it's kind of, it might be counterintuitive to you because we're saying, hey, it's over 50% chance that it's going to rain on each one of these days individually, correct? But the probability that it's going to rain on both days is actually less than 50%, all right? So this is going to happen with probability. When you multiply two numbers together that are less than 1, it's going to make an even smaller number, okay? And the reason it's going to make it even smaller is because we have a lot of other possibilities here than yes, rain on both days, correct? We could have yes, rain on Saturday, no on Sunday, no rain on Saturday, yes on Sunday. And then we could have no rain on either day, correct? So there's 4 kind of possibilities that could come out of this. Okay, and so let's talk about the other possibilities. So what's probability that rains on Saturday? So rain on Saturday is 0.6. And then no rain on Sunday. Okay, so we want no rain on Sunday. So now we're going to go back to our formula for the complement. So the complement would be 0.3, correct? Because it's saying that if it's a 70% chance for yes on Sunday, it's a 30% chance for no on Sunday. All right. So now we'll multiply those two together. We get 0.18, which would be 18%. That we get a yes rain on Saturday, no rain on Sunday. And then what's the probability that it doesn't rain on either day? So that would be 0.4 for Saturday and 0.3 for Sunday. So that would be the complements on both of those. So that would be 0.12. That would be 12%. Shoot, I should have added this in here. Let's add this now. Let's do one more, okay? Let's do part D, because I want to show you something. What's the last one we didn't do? No rain Saturday. Rain Sunday. So let's add that one in there just because I should have done that. This is like my first kind of year using I just made these notes like last week. So next year when I reuse these notes, I'm going to add that in. So what would be the probability for no rain on Saturday and rain on Sunday? So that would be 0.4 on Saturday and then 0.7 on Sunday. So that would be 0.28 or 28%. Okay. So there is all of our possibilities. Rain on both days, rain just on Saturday, no rain, and then rain just on Sunday. And I wanted to show you this because what do you think that all of this adds up to? All of this adds up to 100%. So the sum of all the probabilities of everything that could possibly happen is going to add up to 100%. When we kind of did that with just one day, rain versus no, it was just 2 items, right? But now that we're doing 2 days, it's really 4 different possibilities, but their probabilities all add up to 100%. Okay, so that's pretty cool. That means you found, yeah. So Danny's saying if you do notice that all your percentages add up to 100%, that means you found all of the possible outcomes. And I would say yes, that does mean that. Okay, so we did this because we assumed that the rain on Saturday and Sunday were independent of each other. But what if you did not know that, right? Can you prove that 2 events are independent? And yes, you can. Here was our formula that we got up here, right? If A and B are independent events, then the probability of A and B equals probability of A times probability of B. So if you're not sure if events are independent, you can prove they're independent by testing this. Does the probability of A and B equal the probability of A times the probability of B, okay? So now we're going to do that. We're going to test independence here, okay? So we have our favorite diagram for this section or for this unit, which is the Venn diagram. So it says we have 1,000 patients with hypertension. 500 were given an experimental medication, and 500 were not given any medication. So they usually do this when they're testing new medication. They give it to half the people and they don't tell who they're giving it to. So they can kind of test, well, what would happen if they took nothing versus what would happen if they give us this new medication, okay? They actually did this with the COVID vaccine when they're doing a year ago when they were doing the early preliminary tests on it. There were a lot of half of the people that signed up for the trials got a shot with nothing in it, like, or it was like water or something that's not going to actually affect you, and then half of them got the vaccine, and then they compared the people who got the vaccine versus the people who didn't. So this is how they test new drugs. This is like standard procedure in medicine, okay? So based on the events, based on the results, are the events on medication and lower blood pressure independent? So what we need to test here is the probability of on medication and lower BP, lower blood pressure. Does that equal the probability of on meds, on the new medication, times the probability of lower BP? So we're going to calculate these two sides independently, and we're going to see if they equal each other, okay? So the first one, what's the probability that you're on medication and you have a lower blood pressure? Well, for this, I would say how many people are on medication and have a lower blood pressure? I would say 135 people. The 135 people in the middle here, all those people fit into both categories, correct? They're on the medication and they have the lower blood pressure. And so that is out of a total of how many people? Well, we had 1,000 patients, it said, right? And so if we divide that out in the calculator, I actually know that's going to be 0.135 or 13.5%. All right, so now let's do this side. I'll go ahead and do this side in blue just to kind of differentiate here. So now we need to do separately. And so let's forget about the left side now. Forget about that 13.5%. I'm just going to put it off to the side. We'll talk about it later. On the right side, what is the probability that someone in this whole group is on medication? So out of the 1,000 people, they actually told us that 500 of them were given the medication, right? So if I'm just talking about being on the medication, it's 500 out of 1,000. I could have also gotten that by adding together 135. Oh wait, sorry, yeah, 135 plus 365. We could have added those together to get that 500 as well, because these 365 plus the 135, they are all on the medication, correct? But also they told us that 500 were getting it. So either way you want to look at that, don't care. Okay, lower blood pressure. So for this one, I am going to have to add together these. So I'm going to go ahead and add those together. 135 plus 245 would mean that 380 out of 1,000. So if I'm forgetting about the medication now, just who got a lower blood pressure, it was 380 people. Some of those people were on the medication, some were not, right? Okay. All right, so I'm going to multiply those two together now. So 500 over 1,000 times 380 divided by 1,000. And so this comes out to 0.19 or 19%. Okay, so we've kind of done all the math we need to do. Now we just need to interpret this, okay? So we're technically not done. We have not answered the question yet. The question was, are these two independent of each other, okay? If when we do these two calculations, if the answer is the same, then they are independent, yes. If they are different, then they are not independent, okay? So I would say here, 13.5% does not equal 19%. Therefore, the new medication and lower blood pressure are not independent. Therefore, the new medication and lower blood pressure are not independent, okay? So that's gonna be my answer in terms of math. But I'll tell you guys, in terms of like what this question is actually asking, what does that mean? To me, it means the blood pressure medicine works, okay? Because if it was independent, that would mean that it didn't even matter if you were on the medication or not. You would have the same probability of your blood pressure going down. And so then it would be independent. But we're saying it's not independent. If you took the blood pressure medicine, you are more likely to have lower blood pressure than somebody who did not take it, okay? And therefore, this is probably a good indication that the blood pressure medicine is working, and so we can move forward in the trials or whatever, okay? So that's kind of the bigger picture of what we're looking at here, because they do these sometimes, and some people's blood pressure just goes down naturally without medication, and so they're kind of testing that against this medicine. All right, cool. All right, let's continue on here. Okay, so now we're going to do what's called table probability. So instead of a Venn diagram, we're looking at a table here. So you can kind of read the table here. So we have 0 checked bags versus 1 checked bags, and then bronze status versus silver status. So question A here says, what is the probability that a randomly selected passenger is bronze status who has 0 checked bags? So what I want is someone who is bronze status and who has 0 checked bags. So that would be these 4 people right here, correct? Then on the denominator is the total here. I could have put, I'll go ahead and calculate this out here. So the total is 10 up top, 9 on the bottom. So that'd be 19 people, right? So I'm going to say that that's 4 out of 19. If we type that in a calculator, it would be 0.211, so about 21.1%. All right. Next question, what is the probability that a randomly selected passenger has 0 checked bags? So for this one, 0 checked bags could actually be either of those two, right? So I would say this one, our numerator is 10. And again, out of the total of 19. So that would be 0.526 or about 52.6%. All right, next question. What is the probability that a randomly selected passenger is silver status with 1 checked bag? Okay, so now they give us 2 stipulations again, kind of like part A. So silver status with 1 checked bag. I think that would just be those 5 people right there, still out of the total of 19. All right, now this one gets a little tricky here. Conditional table probability. When you see the word given, okay, notice how I put that in all caps there, given. So when they have the word given, it really, oops, sorry about that. It really changes how we do these problems. So let's read this one. What is the probability that a randomly selected passenger has silver status given that they had 0 checked bags, okay? So when it says that word given, you assume the truth of that statement. We're only going to be looking at the people who have 0 checked bags, okay? So in the rest of this question, part D, I'm only looking at the people who had 0 checked bags. So if there is only people with 0 checked bags, how many people are there? What's our denominator? And I usually do our denominator first here. So the denominator here is only the people who have 0 checked bags. So it's no longer 19, it is now 10. Because again, when it says given they only had 0 checked bags, I'm assuming the truth. I'm assuming they're only looking at people with 0 checked bags, okay? Then, now we're gonna look at the silver status. But when I look at silver status, it's not everybody in the table. It is only out of these 10, out of the people who had 0 checked bags. That's why I like to do the denominator first, because that's like restricting everyone I'm looking at. So I'm just looking at these 10 people up here, okay? Out of those 10 people, how many were silver status? 6. So 6 out of 10 would be 0.6 or 60%. Okay, now next question. What is the probability that a randomly selected passenger has 0 checked bags given that they were silver status? So it looks like the same question because we're talking about silver status with 0 checked bags, but the order got switched, correct? And so that does change the question. This is a different question. We're gonna have a different answer than our previous question, okay? So when it says, given that they were silver status, that means we're only looking at the people who have silver status. That means this is our whole population we're looking at. So our denominator is gonna be 11, all the people who are silver status. Our numerator is gonna be out of those 11 people, how many people had 0 checked bags? 6, right? So when you switch the order, actually the numerator is going to stay the same because that's like the one that is kind of both. But the denominator will change because it's based on, our denominator is based on what's after the given, okay? So for that one, we get 6 out of 11. And we get 0.545, which will be about 54.5%. All right. All right, I don't think we'll have time for the coffee problem today. So we're gonna go ahead and pause here and we will finish this up tomorrow, okay? Please do not submit your notes yet because we wanna submit them complete. So let's finish them up tomorrow and then we'll go ahead and submit them and get our points for them, okay? No homework tonight, but as always, if you have any missing assignments, this would be a great opportunity to get some of those made up on Schoology, and then I'll get them updated to areas as soon as I can, okay? Today, no. Every teacher is different for deadline for missing assignments. So if your other teachers told you something different, definitely go by what they said for their class. For me, I'll take it up to the day of the final. It's fine, but don't fall behind because if you have a ton left over, it's gonna be tough to make them up, okay? We'll talk about that more tomorrow. How about that? All right, I think that's all I got for you. So I'll stick around a minute for questions, but if you don't have any, we will see you tomorrow. All right, bye.